Hello everyone, I'm glad to give this report about a cost-effective tangible rehearsal interface for microsurgical clipping of intracranial aneurysm. Intracranial aneurysm is a cerebrovascular disorder which poses a severe threat to life. Microsurgical clipping is one of the primary treatment methods, aiming to prevent the brain aneurysm from rupturing by using a metal clip to occlude the neck of the aneurysm. Microsurgical clipping presents several challenges, while a virtual rehearsal system offers a great solution, allowing surgeons to practice in a reusable environment and gain the skills needed to perform surgeries effectively and safely. There are several commercial surgical simulation platforms available, like surgical theater, dextroscope, and immersive touch. In addition, there are custom VR simulators built using open-source software such as Blender, Unity 3D, and Sofa, among others. However, existing simulators have some drawbacks. Commercial platforms are expensive, and many studies use only a limited number of aneurysm cases. For aneurysm clipping, some simulators only focus on clip placement, ignoring the interaction and deformation between the clips and vessels. Additionally, most simulators rely on desktop haptic devices, which don't provide the same tangible feedback as real surgical instruments. Our objective is to create a tangible interface using real surgical instruments, simulate vascular and aneurysm interactions in real time, and generate patient-specific 3D aneurysm models in an expandable way. The picture shows our MR-based virtual rehearsal system. We developed the system by reconstructing a high-fidelity microsurgical environment, which fuses virtual patient-specific anatomy and real microsurgical instruments to enhance the user's spatial perception and tangible stimuli. To create patient-specific 3D aneurysm models, we first focused on reconstructing a 3 cm cubic region centered around the aneurysm. After that, we integrate this localized model with the standard brain model. Before we do the staging, we use a scaling constraint SCP method to register the lesion-specific model with the relevant vascular segment in the standard brain model, as shown in the figures. For interactive microsurgical clipping simulations, we used OBI toolkit in Unity to generate low-resolution particle samples from the 3D mesh model, speeding up the simulation of vessel deformation after clipping, as shown on the left. Next, we apply collision distance constraints within the position-based dynamics method to simulate aneurysm vessel deformation. This helps reduce penetration during two tissue interactions and improves deformation stability. The pseudocode for this is shown in algorithm 1. For high-fidelity tangible interaction, we first attach two markers to the legs of the clip holder. Then we use RealSense to track these markers and interpolate frames to match the recognized gestures, mapping the real clip holder to the virtual one. To speed up detection, we optimize the process by calculating a sub-figure around the markers, as shown in red block in the figure, instead of using the original detection method as shown in blue. Finally, using an HTC Vive HMD and a controller, we integrate all of these techniques into an MR system for virtual rehearsal. We also design an intuitive control panel, which includes 4 key functions. For the experiment and evaluation, we begin by focusing on specific to general registration and staging. We worked with a chief neurosurgeon to select typical frames from real surgical videos and find the matching views in our simulator for 3 IA cases. As shown in the figure, Table 1 shows the accuracy of our registration algorithm. We measured the similarity between the lesion-specific model and the standard brain model using the mean squared error. For the vascular deformation simulation, the figure shows the clipping results for 3 typical IA cases performed by surgeons. In Table 2, we present the system's frame rate during simulation. The results show that for our current simulator cases, the average simulation time is more than sufficient to support real-time interaction. We also compare 3 different methods: the baseline PBD method, the PBD method combined with shape matching, and our approach that includes condition distance constraints. As you can see, compared to the PBD and the PBD with shape matching method, our approach, which incorporates collision distance constraints, effectively prevents any penetrations between the clip and the blood vessel during interactions. For macro-based instrument tracking, we placed and fixed the clip holder in different positions and tracked its pose over time. We then calculated the errors in position, rotation, and delay, as shown in Table 3. The results demonstrate that our optimization module significantly reduces the time needed to detect the clip holder in various positions. We invited 10 surgeons to test the rehearsal system and conducted a post-task questionnaire to gather their feedback, as shown in Table 6. We used a 5-point Likert scale to assess the system, as illustrated in the figure. Overall, the rehearsal system received positive feedback, with users highlighting strengths in the clarity of the user interface, instrument accuracy, and spatial perception. We also assessed the perceived workload of performing the clipping task in our rehearsal system using the nasal TLX, as shown in the figure. Overall, the workload of the system we designed was considered moderate. Participants generally felt that the mental demands were higher than the physical demands, especially during the clipping task. For the assessment of the clipping task, as shown in Table 4, only acceleration and the jerk showed significant differences, which indicates that compared to the residents, the neurosurgeons demonstrated greater stability in controlling their hand movements. Here we will demonstrate our system. First, we have the system's functionality controlled by a controller that emits rays to switch between aneurysm cases. We have preloaded 3 cases. Then we show how to switch the brain model's rendering mode. The transparent mode allows for better spatial perception of the lesion area. At the same time, the controller's dial can be used to move and rotate the model. To simulate the clipping procedure more realistically, we switch to the microsurgical view. The system has 2 types of the clip models preloaded, and they can be flipped based on the surgical approach. Additionally, we have set up a one-click option to remove incorrectly placed clips. Next, we showcase a neurosurgeon using our system to perform the clipping procedure. Finally, we demonstrate the aneurysm deformation simulation in a clipping task under the microscope. In conclusion, we have developed a novel MR-based rehearsal system for eye clipping, built on a tangible interface that closely mirrors real surgical scenarios. The system allows for real-time and accurate deformation simulations as the aneurysm clip interacts with the vessels. Additionally, it generates patient-specific 3D eye models in a cost-effective way, making it quick and easy to add new cases. However, there are still some challenges pointed out by the surgeons. Our plan is to address these issues in future versions of the simulator to enhance its overall effectiveness. Thank you for your attention.